Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 14 on gases and 14.2 about gas laws. We are in Part 4. So today we're talking about the ideal gas law. So we know that pressure times volume divided by number of moles times temperature is equal to a universal constant. So P1V1 over N1T1 is equal to P2V2 over N2T2, and we put it all together with our constant PV equals nRT. All right, for gas problems, there are two types of gas problems. One where the conditions change in one scenario versus the others. And then another one is where the conditions don't change, you just have to solve for one of the variables. So, for the gas problems with an unchanging condition, you find the universal gas constant, and then you convert all your known values to the same units as the R, and you write the equation PV equals nRT. You substitute in your numbers and solve for the unknown. Okay, so please write down this question. What would be the pressure inside a 50-liter tank containing 1,252 grams of helium at 20 degrees Celsius? All right, so let's look at our problem. So what would be the pressure? So we're looking for the pressure inside a 50-liter tank, which we know is our volume, containing 1,252 grams of helium at 20 degrees Celsius, which is our temperature. And then I know we're supposed to find N, our number of moles, but that isn't number of moles, that's grams. You can convert grams into moles. All right, so let's write down what we know. So our pressure is our question mark. Our volume equals 50.0 liters. Our temperature is 20 degrees Celsius. Let's do our conversion. Plus 273 Kelvin equals 293 Kelvin. All right. And then N, calculate moles of 1,252 grams. Okay, so let's do that first. So I have 1,252 grams of what? Helium over 1 times 1 mole is what I'm converting to, 1 mole helium, and then my molar mass of helium, because grams are going to go at the bottom, is 4.00 grams helium. So then the grams helium cancels out, and I'm left with how much? (313 moles helium. So that equals 313 moles. All right, so then after we figure out what we have, put all of our conversions into units, we're going to figure out our R. So you'll need to look on page 459. There is one R that is 0.08206, which is in atmospheres times liters over moles Kelvin. There's another R, which is 8.3145, which is pascals per cubic meter over moles Kelvin. So let's see. Our pressure Well, we don't know our pressure, what it is, but our volume is in liters. So we'll have to use the one that's 0.008206. So let's write our equation. PV equals nRT. And so our pressure is what we're solving for. I'll move it over just a little bit. Our pressure is what we're solving for. Our volume is 50 liters, 50.0 liters, which is equal to our number of moles, which is 313 moles, times our constant, so 0.0820, where's it, 8206. And that is atmosphere liters over moles Kelvin times our temperature, which is 293 Kelvin. So simplifying here, we're going to take 313 moles. Well, we know moles is on the top, and it cancels with this one on the bottom. And Kelvin is on the top, so it cancels with that one. So we have our pressure times 50.0 liters, which is equal to, and then you'll want to simplify what's on that side. So take a minute and do that. Okay, so I get 7525.6 atmospheres times liters. And then I'm going to divide each side by 50.0 liters. And what do I get? My pressure is equal to, so take a minute and solve that. And so I get 150.5, and if we look at 50.0, 50.0 has 3 sig figs, and this one has 4. We're going to not look at the temperatures, so 3 and 4, so we get 3 sig figs. So 151, and then the liters cancel, and I have atmospheres. All right, so let's take a look and see if that seems reasonable. What would the pressure be? Yes, inside of a 50-liter tank containing 1,252 grams of helium at 20 degrees Celsius. So we know 1,252 grams is 313 moles, and we know if it's at 1 atmosphere, it would take up 22.4 liters. So if it was at if there was 50 liters at 1 atmosphere, it should take up, it would take up about 50 liters. And then it's more than that, so it must be at a very high pressure. So is this at a very high pressure? It is. Very good. You got a reasonable answer. Okay, we just used the ideal gas law. But what happens if the conditions are changing? What do we do? Well, first, we're going to use the equation and substitute in all known quantities. P1V1 over N1T1 equals P2V2 over N2T2. Then you cancel out any properties or quantities that stay the same. So if the temperature doesn't change, you get rid of your T's. And then there should be one unknown after you do all those things, and you solve for it. Okay, let's do it. What would be the new volume of a 0.050 cubic centimeter bubble in bread dough once it goes from room temperature, 20 degrees, to 191 degrees Celsius oven? So let's tackle that. Okay, first thing is to see what we know. So what would be the new volume? So that's going to be V2. And then we know the original volume is this 0.050 cubic centimeter bubble. And then we know the original temperature was 20 degrees and the final temperature is 191 degrees Celsius. So let's write those out. So V1 equals 0.050 cubic centimeters. V2 equals our question mark. And then T1 equals 20 degrees Celsius, and then we're going to convert that to 293 Kelvin, and our T2 equals 191 degrees Celsius, and we're going to convert that into, that's going to be 4, 9 and 9 is 8, carry 1, 2, 3, alright, so it should be 484 Kelvin, and let me double check that. Okay, good thing we double checked that, because it's not 293, that's not our conversion, that's the answer from above. So that equals 464 Kelvin. Alright, so then we're going to write our equation. If you notice, we don't have R, we don't have a constant in here. So using cubic centimeters as for your volume, you don't need to convert it because you don't have a constant with that unit or a different unit. So as long as you use the same unit at the beginning and the end, that's fine. You can leave it in cubic centimeters. So we have P1 V1 over N1 T1 is equal to P2 V2 over N1 T1. So the question is, what do we know? What stays the same? Pressure. Is the pressure inside and outside of the stove going to be the same? Yeah, it should be about 1 atmosphere. Volume, well, no, that's what we're solving for. So V1 is, I'll just write the P1, we're going to cancel out, and the volume is 0.050 cubic centimeters equals, and then are the number of moles in that bubble going to be the same inside and outside of the oven? Yes, it is. And then the temperature we know is going to change. So I'll cross that out. So the original temperature is 293 Kelvin. Okay, and then we know we're canceling out pressure. And our V2 is what we're solving for. And our N1 we're canceling out. And our T2 we know. Okay, so what you'll need to do is simplify the left side and the right side. So take a minute and do that. Okay, so you should get something like 1.706 times 10 to the negative fourth on the left side, and then equals V2 over 464 Kelvin on the right side. So these cancel out, and then you get V2 is equal to, and take a moment and solve that. So you should get something like 0.079, and we get 2 sig figs cubic centimeters. So our bubble got a little bit bigger. Okay, to finish it up, we're going to discuss chemistry connections, so please write these things down and be ready to discuss them. High altitude training for athletes, breathing at sea level versus high altitude, physiological changes when training at high altitude. And then we are done. Good job.